either really sad or something's going on. Yeah?
Do you have to put a formal charge on the whole anion bracket?
I'll just take a look at what you guys have. I was more interested in you guys connecting the dots from our resonance chapter into our acids and bases chapter. We're going to practice it quite a bit today. All right. So now what we're going to do is we're going to look at equilibriums for acid-base reactions. So yesterday we talked a little bit about equilibriums. And so let's make our generic acid-base reaction. So we've got HA, which is our generic acid, and I'm going to react this with B, our generic base. And this is in equilibrium with our conjugate base right here, and our conjugate acid, our HB+. So this is our acid, our base, our conjugate base, and our conjugate acid. If we look at this, we've actually got two acids in equilibrium, right? We've got our original acid, HA, and then we've got our conjugate acid, HB. And this gives us a lot of hints as to which side of the equilibrium predominates. So let's say HA is the stronger acid. Do you think the equilibrium will favor the right-hand side or the left-hand side if HA is the stronger acid? The right-hand side. So the way we can determine equilibrium position is identify which is the stronger acid. Is it going to be HA or is it going to be HB? The stronger acid will actually drive the equilibrium to the opposite side. And I always like to describe this as a push. What if HA is a really weak acid, but HB is a strong acid? It's going to push it to the left side. It doesn't mean it's going to be 100% on the left-hand side. The whole point of an equilibrium is we've got some relative distribution of the left-hand side and the right-hand side, and we can determine the relative proportion based on the strength of HA versus HB. So let's take an example of this, and hopefully it'll make a lot of sense when we see this. Let me slide this down too.
So since the conjugate acid has a charge,
Yeah, just 1 second. What was the question again?
since the conjugate acid has a charge and it's weaker?
Not necessarily. We're just using generic terms right now, so we don't really know which one's what. We're just using generic terms. All right, so let's take an example, and hopefully this will make more sense in the context of an example. All right, so the example I have is HCl and H2O. This is in equilibrium with our conjugate base, which is Cl minus plus hydronium. So what are our two acids in equilibrium? Yeah, exactly. HCl is our original acid, HA, and then we've got our conjugate acid, H3O+. plus. We've got two competing acids in equilibrium. How can we tell which one's stronger? Yeah, we can look up their pKa values. Do a titration, yeah. You guys seem fond of that. All right, so on the class website, under useful links, I posted a link to a very, very popular pKa table. There's also some pKa tables in your book that you can use, but all of these are experimentally determined values. So what we need to do is we need to find the pKa value of HCl, and we need to find the pKa value for hydronium. So let's go through the chart and see if we can find it. All right, HCl, we've got that over here. It's -8. Hydronium, oh, we got hydronium up here. That's -1.7. So let's go ahead and go back to our reaction. We could say, okay, HCl has a pKa of -8.0. Hydronium has a pKa of -1.7. Which one's the stronger acid, HCl or hydronium? HCl, because it has the smaller or lower pKa, right? So if we look at this, we could say this is the stronger acid. It's going to push the equilibrium to the right. Or, yeah, to the right. So really, we can redraw this equilibrium arrow as something more like this, right? So do you guys ever see equilibrium arrows drawn in your other classes like this? Where essentially the top hand arrow is showing that it's favoring the right hand side, but we do have a little bit of it on the left hand side. So we should show that with the underneath little arrow. You can show it this way if it helps you understand which side of the equilibrium is favored, but it shows that the reaction's mostly favoring the right-hand side of the equilibrium. So if you ever are confused on whether or not an equilibrium is on the right-hand side or left-hand side, look up the pKa values of both acids and then compare which one's stronger, and that'll give you a hint as to which position the equilibrium is favoring. Does that make sense? Yeah?
In practical terms, what's happening here? Is it that if you mix the water and the HCl, when it sort of stops its reaction, you have mostly the H3O left and still some HCl? Is that sort of what?
Yeah, so let's say we take HCl gas, which is in a cylinder, and we bubble it into water. Before we mix them, they're in pre-equilibrium.
Yeah.
As soon as we mix them, it'll take a little while, but they'll reach equilibrium. Once they're in equilibrium, all 4 species are in solution.
Okay.
The question is it a 25, 25, 25, 25 mixture?
Okay.
Or is it 99% on the right-hand side, 1% on the left-hand side? And so the equilibrium is telling us which side is being favored.
Okay.
The reality is all 4 species are in equilibrium, but not usually in equal amounts. Yep. All right. So let's continue on. This pKa table, by the way, is one of my favorites. This was created by Dave Evans, a really famous chemist from Harvard. And then I've also included, I had the link on here. It must have disappeared. But if you go to the quick links on the website, you can pull it up. If you want to print it out and keep it as a reference, it's a really great tool to have for not only this class, but biochemistry as well, if you're taking biochemistry. Okay, so now we've got to continue on to one of the more important parts of this chapter, and that's predicting relative acidity. So what if we don't have a pKa table and we're asked, well, just guess which one's more acidic? This is where things get a little tricky. And again, let's go back to our generic reaction. I know you guys are probably tired of seeing this. But the key is our conjugate base, and this is what I mentioned on our problem of the day. When we're comparing relative acidities, look at the conjugate base of your acid. This tells you a lot about what's going on. So a strong acid has a stable or weak conjugate base. And then various features in a molecule can stabilize that negative charge or the conjugate base. So in our problem of the day, we saw one molecular feature that can stabilize our conjugate base, and that was resonance, right? But there are a handful of other ones. So let's make a list of some important molecular features that can stabilize our conjugate base. So number one is electronegativity. What do you guys think I mean by this?
The more electronegative it is, the more willing it is to be negatively charged.
Yeah, exactly. If we've got a conjugate base that's something like Cl, and it's got a negative charge, Cl is pretty happy with the negative charge. But if we've got something like, I don't know, sulfur with a negative charge, that's not going to be as happy carrying that negative charge because it's less electronegative. So let's take a look at this with some examples and some data. So the first example I have is methane. And I'm going to use a generic base B because we're just focusing on the acids right now. And then the conjugate base for this would be our methide anion plus HB, our conjugate acid. Let's compare this to a different reaction where we've got H2O plus a base in equilibrium is going to form OH minus plus HB. So what's going to be our more stable conjugate base? Is it going to be our methide anion or our hydroxide anion? Hydroxide, right? Because oxygen in this case is much, much, much more electronegative than a carbon. It's happier carrying that negative charge. Conversely, that means that water in this case must be the stronger acid. So immediately, if I gave this to you on the next quiz, I could say rank the acidity of methane versus water, and you could say, well, water is going to be the stronger acid because it forms the more stable conjugate base. And we can rationalize that using electronegativity. All right, so that's one periodic trend that's really helpful. Let's take a look at another trend.
Why is it more stable?
Because oxygen, which has a negative charge, is more electronegative than carbon.
Oh.
Carbon is less electronegative. It's not going to be as happy carrying that charge. Let's take a look at another periodic trend. This is atomic radius. All right, so if you look at the periodic table, does atomic radius increase or decrease as we go down a column? Increases. And so that's an important trend to remember. And so I'm going to throw two examples up, and we're going to try to rationalize the difference between these. So the first one is hydroiodic acid plus a base. So iodine's pretty low on the periodic table. It's going to form iodide plus our conjugate acid. And then we're going to compare this to something like HCl. So in this case, we get chloride plus our conjugate acid. So now the question is, which one's more stable? Is it going to be our iodide or our chloride? Oh man, this is tricky, and it's something that threw me for a long time. Our electronegativity rules would lead us to believe which one's more stable? Chloride. but that's only the half of the story. The other half is the atomic radius. If we think about these as anions, we've got an extra electron in each of these. An electron wants room to roam, right? Which one does it have more room to roam in? Iodide. So in this case, iodide is more stable since it is larger, which conversely means that Hi must be a stronger acid.
So when you have the two things competing, radius beats out electronegativity.
Yeah, and this is something that's tricky. If we're comparing two things in the same row, we're looking at difference in electronegativity. If we're looking at two competing acids in the same column, then we're looking at difference in atomic radius. So we've got two different trends we're looking at. If you're looking at a difference in two acids that are diagonally arranged, things become a lot more complicated, and that's when we would have to rely on a pKa table. So let's go ahead and write our trends up here. So the periodic trend is more electronegative left to right in a row. What's that? But if we're looking at atomic radius, we're saying it gets larger as you go down a column. Yeah, just 1 second. All right, so how many of you guys watched Breaking Bad when that was out? Yeah, quite a few of you, great. You guys remember the scene where he is trying to get rid of a body and he dissolves it in hydrofluoric acid? Is hydrofluoric acid a very strong acid? No, it's not. Why isn't hydrofluoric acid a strong acid? Because if we look at the atomic radius of the fluoride anion, it's very, very, very small. So it's a weaker acid than even HCl. So hydrofluoric acid, a lot of people saw that show and they're like, wow, that's the strongest acid you can get a hold of. Not exactly. It's actually a relatively weak acid, but what it will do is actually react with your bones because it will irreversibly bind to calcium. So that's one big thing that people misconstrue is they always hear about how dangerous HF is, or hydrofluoric acid. Has nothing to do with the acidity, has everything to do with the weird reactivity of fluorine. So I just wanted to throw that out there. All right. Let's take a look at our third feature. So we've done electronegativity, we've done atomic radius. Those were two features that had to do with the atom itself that the charge was on. The third one we've already seen a little bit with. Resonance. So let's compare two different molecules, okay? I'm going to draw out the full Lewis dot structure just so everybody can see what's going on. Let's say we take ethanol and we react this with a base. Which proton's most acidic on ethanol and why? Is this proton acidic? No, because if we did that, carbon would have a negative charge. Carbon's not very electronegative. What about this proton?
Yes.
Yeah, because if we remove that proton, the charge would be on a very electronegative atom. So that means our conjugate base would have a negative charge here, and we'd have HB. Now let me finish filling in these hydrogens. Okay, so this is our one example. Let's compare this to a different example. we've got acetic acid here. We've got our base. Again, we're going to pull off a proton, not from the carbon, but from the oxygen. Which one's more acidic?
Bottom one.
Ethanol or acetic acid? Yeah, it's in the name. That's a good hint. All right. But if we look at just electronegativity, it's a tie between these, right? It's oxygen and oxygen. But the special feature with this one is the negative charge can be delocalized across two different atoms. So we could go ahead and we could say, all right, this one has a major resonance structure. Whoops, this should be a single bond. And this one's negative. And last but not least, we've got HB hanging out over here. All right, so if we look at this, does the oxygen have a true negative charge on it? Yeah, it's a partial negative. It's sharing that negative charge across both oxygens. That means that it's highly stabilized. Therefore, this must be the stronger acid. All right. Now, are you guys ready for a weird one? Yeah? All right, so we've done electronegativity, we've done atomic radius. The next one is called induction. Yep. So if we look at our top one, the negative charge can't delocalize. It's stuck on that oxygen.
Yeah.
If we look at the bottom one, that negative charge can delocalize across both oxygens, which means the oxygen in reality is a negative 1/2, and that makes it much, much more stable than the example right above it.
Because the oxygen means 8?
Because in this case, we're delocalizing the negative charge across multiple atoms. It's not being forced upon any one atom in particular. Yeah, so the more we can spread out charge, the more stable it is. All right, so our next one is called induction. And induction's a really kind of interesting one. And let me explain it before I show you it. Induction describes the pulling of electron density through sigma bonds. And I'll show you guys an example of this. Let's say we've got our acetic acid from our previous example. And we react this with our base, just like we saw above. We're going to get our conjugate base out and our conjugate acid. Yeah, this is pretty stable because we've got our negative charge delocalized. But let's compare this to a different one. This is called trifluoroacetic acid. If we look at these two conjugate bases, which one's more stable, the top one or the bottom one?
Bottom.
Bottom one, right? If you look at the bottom one, it's got fluorine, Fluorine's the most electronegative atom on our periodic table. It's going to suck electron density away from that negative charge, all the way through the sigma bond. So even though it's not a resonance structure, it will actually pull electron density away from everything else around it. It's an electron hog. So the way I typically show this is I show it using a dipole arrow, and that makes it more stable. And we refer to this as induction.
So do those electrons actually delocalize?
No, it's not a true resonance structure. It's more of a weaker pull through sigma bonds. Resonance structures have to do with delocation through pi bonds. Induction has to do with pulling through sigma bonds.
Oh.
Yeah. Yep.
Does this only apply to certain elements, or only certain elements before doing it?
Yeah, so if we're looking at induction, there has to be a very strongly electron withdrawing atom involved. Typically, you see this with fluorine, oxygen, and nitrogen, the big three.
Not like the halogen.
You do see it a little bit with halogens, but it drops off significantly with the halogens. You really don't see induction with carbon and hydrogen, though. They just aren't electronegative enough. But that top right-hand corner, that's where you see induction occurring. Yep.
Can you differentiate between this and electronegativity?
So electronegativity has to do with the atom where the charge is located. Induction is saying, all right, we've got an electronegative atom further away down the chain, and that's sucking electron density away, which stabilizes it. So electronegativity is only looking at where the charge itself is located. Yep.
So there have to be two electronegative atoms like that because fluorine and oxygen is really electronegative as well. So does there have to be those two strong ones for the induction to occur?
Usually you see it where you've got a stronger one pulling electron density away from the weaker one. So in this case, fluorine's more electronegative than oxygen, so it's going to tug on it harder.
So there would be induction between nitrogen and oxygen where oxygen is
Yes, exactly. It has to do with the relative difference in electronegativity, and you'll pull that electron density through sigma bonds towards the more electronegative set of atoms. Yep.
So then let's say that we were comparing the first molecule to say the same one except with the oxygen on the top, there's two hydrogens. And that would mean that the oxygens would be pulling towards the right. That would be more acidic.
I'm not quite sure what you mean by that.
The top one.
Yeah.
Very same molecule except for the second one would be same except for the oxygen on the top would have hydrogen.
So you're saying if we had two hydrogens off of here,
Yeah, but the one on top, not the bottom.
up there?
Yeah.
I'm still not quite sure what you mean by that. Do you want to talk about it after class and we can see if we can clear it up? All right. Sorry, let's do a practice one and hopefully that will clarify any questions that you guys have. I'm not trying to be dismissive at all. Okay. All right, let's take another practice. This one's got fluorine, fluorine. This one's got here. And we're going to compare this to an OH with fluorine, fluorine, hydrogen, hydrogen, and hydrogen. Let me scoot this over. All right, which one's more acidic?
Oh, wait. The one on the right.
Oh, this is tricky. You guys see, all I did was I moved these two fluorines from this carbon over here and I swapped them with these two hydrogens.
That's the one on the left because the fluorines are closer to where the charge is, so therefore it's more likely that it'll go there.
Exactly. If you think about an electronegative atom as a vacuum cleaner, if you're really close to something, you can suck electron density away from it. But the further away you get, the sucking power doesn't really have an effect, right? I know that's a terrible example. Yeah, it's kind of strange. If your electronegative atom gets further and further away, the weaker that inductive force is. Same thing with the vacuum cleaner. If you're up close to something and you're trying to pick it up, you've got a lot of sucking power, but the further away you put the hose, you just aren't going to suck up that dust or dirt.
So the OH is a vacuum cleaner?
No, so in this case, oh man, this is our acidic atom, right? But if we look at the dipole, this dipole is really close to that electronegative atom. This one is much further away. Whoops. Sorry, I've got this arrow going the wrong direction. So if we look at this, the inductive effect weakens with distance. Therefore, if we look at this one, we would say that this is going to be our stronger acid since the more electronegative atoms are closer. It's a pretty unique phenomenon. Usually, inductive effect isn't as powerful as resonance. I'm kind of listing these in order of priority. First thing you should look at is electronegativity and atomic radius. Then you want to go to resonance, and then you want to do induction in that rough relative priority. Normally, when I give you two things, I'm only changing one variable at a time, and I'm asking you to compare the pair. Does that make sense? Okay, so let's do our last one. And then I think we'll be done for the day. So we just did number 4. The last one is hybridization. So let's say we've got 2 hydrocarbons. So we've got our example of methane with the strong base. And we're going to form our methide anion. And let's say we've got a different hydrocarbon plus a base. And we form our acetylide anion. Which one do you think is going to be more acidic? Methane or acetylene? Oh, this gets into a tricky case. If we think about the negative charge, is this negative charge going to be closer to the nucleus or further away from the nucleus than in methane? Closer to the nucleus. Why is that? Yeah, if you think about it, this goes back to hybridization. This has a negative charge in an sp2 orbital, or sorry, sp. This one has a negative charge in an sp3 orbital. Which is the longer orbital, sp2 or sp3? Or sorry, sp or sp3? Yeah, sp3 has a lot more p-like character. It's going to be longer. The sp lobe is shorter and stubbier because it has a higher proportion of s character to it. So if we look at this, we could say that means that it's closer to the nucleus and therefore more stable. So if we're looking at comparing two different atoms and they have a difference in hybridization, the one with more S character is going to typically be more acidic. So let's take another example really quick. Let's say we've got this molecule. And I'm just going to label these as R groups. Which is going to be more acidic, this proton in blue or one of these protons in red? Blue, because if we look at it, it's attached to an sp2 lobe. And so this one's going to be more acidic. But what happens if we pull off the red one? Yeah, somebody said it. If you pull off this red one, you'd have a negative charge here that can delocalize and resonance stabilize. So which is going to be the stronger feature, do you think? Is it going to be resonance or hybridization? Yeah, exactly. Hybridization is usually the weakest feature we look at. Resonance trumps hybridization. So in this case, the red proton's actually going to be more acidic due to hybridization. So the order I gave you, 1 through 5, is the relative priority order when you're comparing acidity. All right, for your problem of the day, you may need to pull up a pKa table. Try to work on it with friends, and then if you do have any questions, feel free to let me know.